Hi guys, I'm going to make a quick video on Deligne-Illusie classes. So Deligne-Illusie classes. And so this is going to be mod p squared. Okay, so let R be the p-typical width vectors of, so let's say this is a perfect field of characteristic P. So this is like, so for, if this is a FP bar, so when K is equal to FP bar, this ring is isomorphic to ZP unramified completed. So this is the p-adic integers with all the roots of unity, where p does not divide n, and then we p-adically complete again. Okay, so this is the maximal unramified of the extension of the p-adic integers, and then we p-adically complete this. Okay, so this is a good base for this type of situation, so then we're gonna take x to be let's say scheme over R, which is smooth. Let's say x0 is over R0, and let's say that so here I'm going to use this notation that Rn is equal to R p to the n plus 1, and then xn for, let's say for x, let's say y, let's do this, yn, for y scheme over R is going to be equal to y tensor R over Rn. And so this is going to be like, so this is equal to y mod p to the n plus 1. Okay, so it's a reduction mod. So this is some notations here. Okay. All right, so this is what we have. So we have this notation. And then we're going to take this in here. And so I want to show you a construction. So the Deligne-Illusie construction. Okay, so it takes these deformations of R0 to R1. So let's say smooth deformations to H1 of X0, and this is the absolute Frobenius. So this is the sheaf of Frobenius twisted derivations. Sheaf of Frobenius twisted derivations. Okay, so there's this map like this, like so. And so this is the Deligne-Illusie map mod p, okay, or mod p squared, depending on how you want to do it, because this is the target's mod p, but the image, this is something mod p squared. Okay, so I want to show you how to construct this map. So this is a good arithmetic analog. So this is a baby version of the arithmetic analog. So the arithmetic Kodaira-Spencer construction. So it has to do with width vectors. So this is kind of these things here, since we're working over arithmetic rings, these are kind of width-finitesimal deformations instead of infinitesimal deformations. Okay. All right. So let me show you the construction now. Okay. So take x1, an element of a deformation of x0 over r0, which is smooth over r1. Okay, and then what we can do is we can cover. So what we'll do is we cover x by. Well, let's do this. Okay, so there's kind of two viewpoints here, and let's just stick to locally ring spaces for simplicity. Okay, so let's take a cover UI of of 0 of x0, okay, for I and I, and then we'll let ui1 to x1 for I and I. So these are both covers by affine opens such that one, okay, that there exists a lift of the Frobenius, and two, that we're going to actually choose a lift of the Frobenius with, okay, so this guy, this guy's going to lift this guy, okay, so this is a deformation here, and then we're gonna choose some phi i's from ui1 to ui1, lifting the Frobenius. So this is the lift of the absolute Frobenius. So it's going to be compatible with, so okay, since there's a unique lift of the Frobenius on this, and so this will be compatible here with this thing. Okay, so it has to be. Okay, and so it turns out that lifts of the Frobenius, let's sharp, okay, from O of ui 1 to O of ui 1. Okay, so they have the form here where you take some local section, okay, and they'll look like f to the p, so they'll be the Frobenius mod p, but then we'll have this this guy here, this leftover stuff, okay, and so this is mod p squared, okay, and there's a certain this guy here is what's called a p derivation, and I'm going to almost certainly make a video on this. Okay, so a p derivation. Okay, so let me explain what a p derivation is. So abstractly, it's just a map from one ring, let's say delta from one ring to another ring, that satisfies. It's like a derivation, right? But it's not quite. It satisfies the following: a plus b is going to be equal to the sum, and then plus, then we're going to have some leftover stuff, let's say minus, and then 1 over p choose j, a to the p, so this is for a, b, and a, right? And so it satisfies this rule, p minus j, b to the j, from j is equal to 1 to p minus 1. Okay, so it's like almost linear. It satisfies this rule. So b to the p, and then so it's almost like a twisted derivation, and then it has to satisfy this. Okay, and so here, for this formula to make sense, we need b to be an A algebra. Okay, so there's just a map of rings, and you can check that this does this. So if you have a lift of the Frobenius, there's going to be a correspondence between them and lifts of the Frobenius. Okay, so here, this guy here is actually going to be a map now from, so this delta I, so this gives a delta I, so this is a p derivation from O of ui 1 to O of ui 0. Okay, so this goes from something mod p squared to mod p. And you can actually see that when you're going to divide, so if you have multiplication by p, so notice here that this thing's only defined mod p because we're going mod p squared, right? So when I multiply by p, right, if I had another plus p here and I multiplied by p, it would get killed. So this thing's defined mod p. Okay, so this gives us a p derivation, and now I want to, so a lift of the Frobenius is equivalent to a p derivation, and now I want to define the Deligne-Illusie class. It turns out that of x1, okay, So this guy is a Czech cohomology class, which is the difference of these two p derivations, which lives in H1 of x0. And this is the pullback. So these are, and this is the sheaf of Frobenius derivations. So this is the construction. So I'll probably I'm going to make another video on probably p derivations and these type of things. I just wanted to say this because this is going to come up in when I talk about Deligne-Illusies and in the derived Cartier isomorphisms and essentially this sheaf. Okay, so again, so what do we have? So this is a construction from here to here. I haven't shown you that the difference of two p derivations is actually a derivation of the Frobenius. But it essentially follows from these rules. All right, thanks for watching. I'll post a link if I make a video on this stuff.